They never meet, they never mate, so the timing's off, mechanically doesn't work, behaviorally doesn't work. They're in different locations, never meet. If they do, it might be they meet and they mate, but can't have babies, so that's gamete incompatibility. They meet, they mate, and they have babies, but the babies have a problem, so the hybrid dies in viability, or the hybrids are sterile, like a mule.
Get that set up when you're finding?
Sure.
So if any of that stuff happens, we have a barrier.
Oh, you're actually.
Barrier
Oh,
divides
sorry,
them up,
Becca.
And then we have speciation when that barrier becomes permanent. It's just a tripod there. Oh my goodness.
Welcome, Becca.
I'm gonna walk in front of it. Oh.
Thanks.
Okay, the zebra horse is real.
No, it's not.
Yeah, those are real. Okay, and I don't know. Whoa, very obviously so true. And then
Okay, I do want one of those.
very good. Okay, there we go. So, all right. Now this can happen. These dividing things can happen in different ways. And so we're going to call these modes of speciation. And the modes, we're going to first do some vocab. Pater is father. Patrician is a fatherly figure. And so we'll just do a little English for a minute. We'll get some Latin roots. This is a Greek root. Patra means father in Greek, or fatherland. Read some, maybe some Greek mythology, and there might be an example of patricide, where someone kills their father, right? Okay, so pater and patra mean father. Then we have allo, which means other, something different from. If I were burned and received a skin graft from another person, that would be an allograft. If I burned my arm and they gave me a skin graft from my own leg, that would be an autograft.
An allograft.
Right? An allograft or an autograft.
Yeah, I have someone else's ligament in my knee.
So that's an allograft. Para
Oh, I thought you meant like.
means nearby or close to. And we're talking about both figuratively, it's close, or literally. When we say paramedic, that's literal. They're the medic that's close. They're the one that gets there first, the paramedic. That's the fast arriver, the first responder, we call them, right? So para means beside you, they're near. And then sim means together. You recognize this. So a sympathy. Pathos is feelings, and sim means together. So, oh, you're sad? I have sympathy with you, so I'm sad too. Or you're super happy. I have sympathy with you, so let's celebrate. Right? So same, or togetherness. So now we're going to take these and we're going to dump them into the concept of speciation. Okay? So allopatric speciation. Allo means different. Pater, in this case, means land. Different fatherland or country. Different country. Allopatric. Different country. There's a physical barrier, a big river, an ocean, a mountain range, something that separates them. And it ends the gene flow. And so we're going to look at some creatures that are similar in a lot of ways, but they've been separated by huge, huge distances and oceans. The llama, the vicuna, and the camels. They are related genetically, and they're descended from a common, ancestor that looks a lot like them. But now they can't interbreed. They've been apart long enough, they've lost the common genes needed for them to interbreed and be fertile. So I want you to notice a pattern. Right? The main pattern to remember is you survive the local conditions, but the cost is loss. you lose genes from your ancestors. Okay? And so the result of this over history for most species leads one direction to extinction. So the rule is extinction. The things that are alive are the exceptions. Okay? They have retained enough genes that work to continue going, and the mutations have not damaged them to the point where they're extinct yet, and the natural selection has not put so much pressure on them that they have failed to reproduce in a generation and disappeared. Okay, so, but anyway, we look at these three, and right, we've got South America and Asia. And so you just go across the ocean, so they're separated by huge distances. Archipelagos are fun places to find this because there's islands that are just far apart enough that a lot of the critters can't get there normally, but there's still storms and things that knock them back and forth. And so you'll see different things, different creatures on different islands, very similar to each other, but no longer able to interbreed because of the distances, and that's allopatrism. And so here's a great example of some of these birds, right? And so these are all related, and here's all these islands where they're apart, and you just look at them all. You've got different, different bills, right? Different coloration, all kinds of stuff going on, but they're genetically descended from a single population of birds that had a whole bunch of genetic diversity in it, right? And then they have some of that diversity, they've recombined it, kind of reworked it, and gotten different from the parent birds. Now sometimes they're in the same place, same country, and either they're bordering each other, so they're close together, that'd be sympatric, or they're totally overlapping. They're in exactly the same place, and that would be parapatric. Oh, I'm sorry, I got that backward. Sympatric is exactly the same place. Sympathy means together. And then para is next door. They're really close. So, sorry, I misspoke. But so we'll look at sympatric in the same country. Same country. So they're in the same home range. They are in the same location. There's no physical barrier. What could happen is a drastic mutation that instantly makes a species incompatible with anything else. So a single individual is produced that has a drastic mutation, like a duplication in chromosome number. Now, most of the time that's fatal, but in some plants and certain animals, that can occur, and then instantly you got a new species. And they can only breed with each other, and so there has to be kind of a first pair of them at least to get that started if it's sexually reproducing. So polyploidy can do that. And on Lord Howe Island, there's a bunch of palm trees. They all grow together on the same island, but they can't interbreed because of their genetic differences that have happened. So they're the same land, but for some other reason they can't interbreed. So here's an example of wheat. So people have been cultivating wild wheat for a long time, and interbreeding it with other different kinds. And so have 7 chromosomes, and two of each, 2 from mom, 2 from dad, and all that, and hybridizing it. At some time, we don't know exactly when, but it's before we have good written records, so it's tough to know precisely. But a good while ago, there was a hybrid that formed spontaneously by chromosome doubling, and so this is wild emmer. And what happened is there was a hybrid of 2 different species, and it just kept all the chromosomes of both of them. So it went from having 14 in the male and 14 in the female to having, like, everybody has 28 chromosomes now, which is unusual. They were compatible enough that somehow that worked well. And in fact, it was quite a hardy species, and it produced more grain. And so it was selected by humans then as a good one for food. And they continued to grow that in cultivation for a long time. But again, a crossbreeding occurred and produced a wheat that has 42 chromosomes. So let's just throw in extra chromosomes again, right? And now I want you to notice something. If you're a farmer, you want to plant this one and harvest, or you want to plant that one and harvest. I mean, think about it. The same spot, you're going to get a much higher yield, right? And so farmers then, of course, they're smart, so they choose these to plant. So on the same land, they do the same amount of work, and they get 8 times more food. So the yield is really improved. We need to think about this too. When we talk about, farming, in a traditional fashion, it's not really possible to just go to all the old forms of wheat and grow enough food to feed everybody. You can't do it. Also, if you don't use some amount of synthetic fertilizer, not saying you have to use exactly the same amount that we're using today, but if you don't use a pretty good amount of synthetic fertilizer, you can't get the crop yields high enough to feed everybody. So the human population now, we're in a position where we need to use all the technology we have, including synthetic fertilizer, because if everybody right now just dropped and went all like 100% old-fashioned and organic and everything,
Over half our population would die.
we wouldn't be able to make enough food. We literally just couldn't. It doesn't work. The math doesn't work. So that's not a choice. And then I also heard somebody talking about how then in order to grow the same amount, you would have to increase the amount of acres that you have farmed. And so it would damage the environment even more because you would have to clear a lot of forest land and do a whole lot of other stuff. So we're really in a position where whenever you hear somebody say something like all, right? That's like a very, all of the stuff should be organic, or all of the stuff should be, this or that. Ban all the GMOs, right? Or whatever. That, we need to be smarter than that. We need to understand the pros and cons of all of them and do the engineering thing. What's the engineering thing? The engineering thing is, hey, I can't have, an airplane that gets super, super efficient fuel consumption and is safe. I have a trade-off. I can't have an airplane that's 100% safe, like it can crash at 700 miles an hour and nobody's hurt at all, because I can't do that. So you got to decide what's the trade-off, right? So I got to have some safety, and I got to have some fuel economy, and I got to have some other stuff, and I have all these competing things, right? So what is engineering? Engineering is figuring out a compromise. Engineering is not maximizing everything. It's getting the goal in the best way possible, which means compromising a whole bunch of things. So if we want to feed people the best and take care of the land the best in a sustainable way, we're going to have to use a whole bunch of technology. We're going to need to use synthetic fertilizers. We're going to need to use pesticides. And we're going to need to use them wisely and not overdo it. Overdoing it is a terrible idea too. But, we've got to be smart about it. So, yeah.
Do you personally believe that GMOs pose a threat?
Every GMO should be looked at separately, right? A genetically modified organism, is it going to make a protein from another species? Okay, well, what is the protein? Is that protein safe for this application? Right? Is it for food? Is that protein safe to eat? And just check it out separately. Because it's certainly possible you could make a GMO that was not safe to eat. That would be easily possible. It would make a protein that would not be a good thing for anybody to eat. But golden rice is a great example of a GMO. Rice doesn't make vitamin A. Natural, it doesn't do it. Golden rice has a gene from another species in it, so when it grows, it's actually kind of a little orange, and it makes vitamin A. And so there's a whole bunch of folks in third world countries that can't get vitamin A. It's not anywhere in their local diet, and they're really deficient, and they grow that rice. good for them. So what does it make? Well, it makes a protein that helps synthesize vitamin A. That's safe for humans. That's a GMO, but that one's safe. So that one should be used. Right? By the way, companies that are making GMOs, their goal is to make them safe. So they're not releasing them until they test them. And I get it. If you don't trust them, we'll have other people test them and double check. That's fine. You don't trust a company, because they have a conflict of interest. They want it to work. So go ahead, have independent testing. I'm all for knowledge. I'm all for information. Independently test everything. We should all know everything about what's going into our food. No secrets about that stuff. And then you make the decision based on the knowledge, on the evidence and knowledge. Yeah. And then I think part of it is people just don't know what it is. Because if somebody says ban all GMOs right now today, that means all the insulin-dependent diabetics don't have insulin, because that's all from GMO.
None of they wouldn't be able to have. We'd no longer have beef or pork or chicken or any of it.
Yeah, a lot of things would go away. Yeah. And by the way, do you think this is growing tons of this stuff? That means natural, right? It's natural. That's great. But growing tons of this stuff is also artificial selection. We're choosing. And so when we look at all the farm species that we have now, they're not that similar to. I mean, they're much changed from just selective breeding, and that doesn't have anything to do with GMOs. Just selective breeding changes them a huge amount. All right, so here's the palm trees, St. Patrick on the same island. They're the same location, but they're unable to interbreed because of genetic differences. So there's Lord Howe Island. Looks like a cool. I wonder if that's where they filmed, that old Robinson Crusoe movie. I reread that a while back. It's great. It's just such a good book. You haven't read Robinson Crusoe for a while. Don't read the kid version. Get the unabridged. Get the real one. It's really good. All right, Parapatrick, nearby. They share some border and maybe overlapping habitat. They're nearby. Hybrids in the contact zone between the two groups have lower viability than the purebreds, on the opposite ends of the range. And it's not super common to find this, but we do have some examples of parapatric speciation where they share some land, they interbreed where they meet, but it never, the gene flow from the two populations never is complete. There's a little bit of a barrier because the hybrids are not as healthy to survive and reproduce as the others. So parapatric, bordering or neighbor lands, think of it that way, they're next door to each other.
So if you have animals in different states but in the same country, is that what that's considered, or?
It would be where you have two populations of some critter, and kind of where they meet in the middle, they interbreed.
Okay.
But these stay the same, and these stay the same, and in the middle, you have a few that are different.
Oh, okay.
But it never starts flowing back and forth the whole way. So in this case, we've got a couple of these. I think these are nudibranchs, and they're reproducing here. There's a northern one on the coast, there's a southern one. There's a little hybridized zone in the middle, and the hybrids don't do really well. So the hybrids never get all the way south and never get all the way north. They're just a small area where they occur. And most of the breeding, even in this zone, is still just the north population with north and the south with south. There's only occasionally breeding. So here's a good picture. If you want to draw a sketch, is this from your book? I'm trying to remember if I got this from a different book. I got this from a different book. But anyway, here we go. Aloe, different countries, so chop it in half, right? That's the gene pool. Chop the gene pool in half. They stay apart, and when you put them back together, they stay apart forever. Okay? This is communicating that, hey, they're back together, but look, there's no hybridization that happens anymore, no gene flow. Sympatric, within the same location. Within the same location. Now you got two species. Parapatric, a new niche is entered. In that niche, they develop differently, and now we have two. So the barrier is not always a physical mountain range or an ocean or something. The barrier could be other, it could be genetic, it could be any of those other things that would be preventing interbreeding. So, all right. So, speciation varies in some of the details. Why is it that they can no longer interbreed and have fertile offspring? It could be for lots of different reasons, but it follows the pattern of dividing the gene pool. Some barrier, some kind of reproductive barrier, divides the gene pool up. It could be just separating them, or an island in the middle of the other ones, or their neighbors. And then microevolution happens to both of them until they can no longer come back together and interbreed, and that is then a new species. So how do species form? Does one thing turn into another, turn into another, turn into another? In a straight line? No. Something divides, and these change from these. And where's the original information, the DNA, from? The parents, right? Passed down, reshuffled, mutation, modification. So species diverge. They split from what's already there. Okay. So we have to be careful with that, because sometimes we see in the movies, I know science fiction's fun, but sometimes we see in the movies, and we get the concept in our mind that like Jurassic Park, life will find a way, right? And no, if it's dead, it won't, because it's not life. So stop it, right? So they give all these sterile dinosaurs foods, right? And then somehow they figure out how to become not sterile. I'm like, no, if you don't have the genes to reproduce, you don't have the genes to reproduce. You can't just really want to have baby dinosaurs and then really try really hard and mutate yourself. Sorry, it doesn't work that way. So evolution works with what it's given. It's already got a bunch of genes. It gets to work with those. It can tweak some stuff a little here and there with some mutation, but it can't just make a bunch of new stuff as needed. It just works with what it's got and moves that direction. And that's why we see a lot of things that are like, why is it like that? Well, it's because the ancestors look like this. So that's what that species had to work with as it developed over time. That's cool. Okay. Macroevolution are the big patterns, right? There's all kinds of stuff. One species gives rise to multiple, and over time there's major extinction events. And then after those major extinction events, we see often what we call explosions, like the Cambrian explosion, of all kinds of empty space, and somebody can move in. It's like, hey, here's a whole bunch of apartments for rent, and they're cheap, and they're all vacant, right? So a lot of people move in. So we have all these niches open up, and species can just go out in there and get food, water, shelter, space, and all the stuff they need, and then they start facing selective pressure of wherever that is that they are, and we see what we call macroevolution, the formation of new species from existing species. It does leave a big question hanging, and that's going to just hang there for a long time. Evolution creates new species out of existing species. Where the first species come from? Okay. Well, what's the mechanism? Where's the energy come from? Where's the information come from? And all that. And that is going to be a difficult one. Just to say, well, the mechanism is this or that, because we can't go see. We can have explanations that make sense and explanations that don't. Explanations that are more probable, like scientifically, less probable scientifically, and then we can get non-scientific, and we can have explanations that are more probable or reasonable or less probable or reasonable, that are what I would call metaphysical questions, that are not scientific questions, but are still solved with reason and logic. And so you say, well, this sounds like it's reasonable, and that sounds like it's reasonable, and which one's the best explanation? And then you have, I think, have a lot of patience with people, because you have some really, really smart people that are from all observation, like good, motivated people that disagree on that stuff. And so the most productive thing to do then is to just listen. Listen and think, and then talk. Listen and think, and do that in that order, do it in that order, we get in trouble. Because if you talk first, then, but listen, think about what they said, make sure you understand it, and then talk. And disagree. If you don't think they're right, disagree. But I like that model. That model is fruitful and gets a lot of things done and gets to the bottom of things. There's too much, I don't want to point fingers at individuals, but like Bill Nye yelling at people. I love Bill Nye, but sometimes he just yells at people that he disagrees with about non-scientific things. Okay? And there's folks on the opposite side of him, too, that do that. And there's a whole bunch of people that don't, that listen and interact and are productive. Okay? So that's what we want. We're not just yelling at somebody on the other side.
I don't know, my favorite is still Bill Nye setting the world on fire, trying to prove the point of
No, I'm just saying, he's got his whole career is great, but he's got a couple.
No,
he's got a couple instances.
You've seen that video, right? He has a globe, and he's like, okay, I'm done teaching you. I taught you science in 8th grade, and I'm done. Yeah, and he just goes on this tirade and ends up lighting a globe on.
That's fun. That's a comedy deal.
Yeah. It was so good.
But
there's the Bill Nye I've never seen.
So I'm thinking of something else.
Yeah, me too.
So
That's my favorite part.
okay.
I love Bill Nye.
All right. Now we also have the example where things are in a symbiotic relationship, and then selective pressure acts not on one of their bodies; it acts on both of their bodies. So the phenotypes of the two in cooperation are selected for. And we call this coevolution, where you have an interdependence. Well, the predator will die without the prey. The prey would be okay without the predator. They would. However, the prey would have different selective pressure on them if the predator were removed. Host and a parasite.
I think
the parasite needs the host. The host doesn't necessarily need the parasite, but they still evolve together. Because whenever there's a relationship where one of them needs the other one, they evolve as a pair. They evolve together. The selective pressure. Because if the deer changed, the mountain lion's got to change so it can still get food. Okay? A pollinator and a flower. And over time, that dependency can become so profound that they literally will die without the other one. So we now have termites that eat wood all day and can't digest a bit of it. They can't digest wood at all. They have no enzymes in their genome. They don't have any instruction in their DNA to make the enzymes to digest wood. So they eat wood all day long, and that's all they eat. And they can't digest it. But there's protozoans in their gut that eat wood and turn it into carbohydrates that the termites can't eat. And so the termite doesn't have the protozoans, the termite dies. Now it turns out the protozoan then is living in the termite so long that it stops making certain genes that it needs to live anywhere else. So the only place it can live is in the termite's gut. It can't live anywhere else because it needs the conditions in the termite's gut to live, and it can no longer do anything normal. It lost those genes. And so now what we would almost call a parasite, it's not really a parasite because it's doing something good for the termite and it's good for the protist. They absolutely need each other. So now they're stuck, and natural selection acts on the pair of them as if they're one species, but they're two species. So that's a very close symbiotic relationship. Coevolution, they have to evolve together or they all go extinct. So the termite goes extinct, the protist goes extinct, and vice versa. The protist goes extinct, the termite goes extinct. So here is a flower. The flower's nectar tube, the nectar's way down in there. Most moths cannot reach it. But this moth has a proboscis that extends. Check that proboscis. So it can unroll, it's one of those ones that's rolled up on its face. It can unroll that thing and reach way down in the flower with that big, long drinking straw and get the nectar.
My dad's tongue.
Right? So, pretty cool.
Oh, yeah.
Many species don't show much sign of evolution because the natural selective pressures have been the same on them for so long that they don't change much. And we find some examples where, hey, that's a fossil and it's extinct, and then somebody finds it in a fish market. It says, oh no, we catch those every once in a while. Like the coelacanth fish. Like, hey, those have been extinct forever. Oh no. No, they're not really great to eat. They're okay, I've eaten one. Like, what? Yeah, I got it marked over here. Ask that guy, he catches them every so long. And then they go out and they find him, and then they yeah, we hardly ever catch him. We'll save one for you. Give them a little money, right? Save one for you. Then they find one, they get in the museum, they eventually go out there with a submarine, they find some swimming around, they're really weird, interesting, but they're still look the same exactly as in the fossils. I mean, just alligator is a good example. Alligator, modern alligator in the fossil looks pretty much the same. And we call it stasis, stay the same, stay the same, stay the same. And then we have what we call exaptation. And I always have thought, that pre-adaptation is the word that we should be using. Pre-adapted, not things are adapting. They're pre-adapted or they die, so let's call it pre-adaptation. I like that. But we say, well, hey, in this group, the same genes and the same structure does this job. In another group, it was pre-adapted. It could have done a different job, and in fact, it does do a different job in this other group. And so we think of feathers. Feathers do a particular job in birds. They do a particular job in some of the dinosaurs that were feathered dinosaurs. But it was the feathers were there to do either one. They could do either thing. So in one group, they did one job. A different group, pre-existing structure that had different uses. Adaptive radiation is where we see a lot of speciation happen, where new niches open up. Very often, that's when there's a drastic change, like an extinction event, or a volcano rises up out of the ocean, and now there's an island, and we see things colonize a new location, all the job openings. There's a lot of job openings, right? So there's all these niches of land and food available that things can fill. And every so often we identify what we call a key innovation, a new recombination, maybe a mutation combined with a new recombination that produces a structure that's novel and special. Now, the information was there, but now it just got rearranged in a new way and comes out in an unexpected innovation. And so, I think maybe the feather itself is one of those. And that can lead to all kinds of other things. So, a key innovation. Well, we know what an extinction is. They're gone. There are 0 breeding pairs or 0 individuals. They've all died and they're gone. The opposite of extinct means is extant. So the antonym. Extinct is gone. Extant means they're still around. They exist. They're still existant, right? Extant. But we see some mass extinctions in the fossil record where something happened. And our book lists 5 gigantic ones, and then there are some smaller ones. And one of them we call the radiation of mammals after the KT barrier extinction. So you see a rock, there's a rock, and there's another rock, and there's not very many mammals down here, and then you see this line in the rocks, and then there's tons of mammals. Right? All of the modern classes of mammals, the modern orders of mammals, boom. Okay, so there we go, and all these groups just appear and evolve in this, right by this line. So evolutionary biologists are trying to explain how all the species on the planet are related due to common ancestry, and this is a big challenge, because it might be possible there's more than one original life. There could be more than one species to start with. So how do you figure that out, right? And so they're really going to, when they can, use genetic information because that's pretty objective. But the other thing that they use, I have criticized for many, many years, as do other biologists have as well. It's great for sorting, but I don't think it's not strong for giving ancestral relationships. So phylogeny, it's called cladistics. And in a cladogram, you sort things based on physical structure, right? Now, if you do cladistics with DNA, it works better, but you don't usually get DNA for fossils. So we're going to use structure. And the problem with that is you have to decide what structure is more important in a hereditary sense than another one. Is our number of ribs more important than number of wrist bones, right? And how do you make that call? It's subjective. And whenever I say subjective, I mean there's no ruler in which I get a number. I just pick my favorite. So it's not a scientific operation. It's a values judgment. I think that one is a higher value than that one. And now I will say the scientists doing this have a lot of expertise and a lot of knowledge, so they're going to go with their intuition and their gut. So I think their evaluation is probably more valuable than mine, being less trained, but it's still subjective, which means we have no real way of measuring or falsifying it. How are you wrong or right? We don't really have a way of putting odds on it. And so what we do is and I love this because the author in I've got a book on vertebrate paleontology. The author in this is great the way he explains it. Here's vertebrate paleontology. I don't think I marked the right page, but anyway, in here, yeah, you can see when I study something, I mark the book to that. But he's got all these, right, cladistics. He's got these cladograms, phylogenetic trees all over about this descended from these and these and these and these. But also you go to the back of the book and you'll find you have 5, 6 alternate ones. These are all hypothetical. They're reasonable guesses, but none of them are proven. So, and some are more likely than others. Some are more likely, some are more probable than others. But we don't get to know which one's right. So it's going to cause disagreement right here. And we see biologists disagreeing about it. And disagreement doesn't mean we don't know anything, okay? It just means we don't know everything. There's a big difference. Oh, you don't know anything. Well, you don't know anything is a big difference from you don't know everything. Okay, and so we know, we use as much information we can, but we don't have it all, so there's going to be disagreement. I think it works this way, somebody else thinks it works that way, right? And we see eminent evolutionary biologists having those conversations about what they think is going on and sharing that. All right, so we have macroevolution, that's the formation of new species, and we have recurring patterns of this. Pre-adaptation, also called exaptation. Adaptive radiation, extinction, over and over through the fossil record. We look through the rocks and we see that. We see lots of stuff, and then lots of stuff, and then lots of stuff in the layers of rock. And so we know that. All right, just finished with that.
That's not
pretty. Oh,
that
anyway.
hurts me. That's like Jurassic Park meets Lord of the Rings.
I don't know what that is. I just thought it was.
It's Lewis and Clark.
Yeah, I think. Yeah. I don't know. There was a